So far we've been talking about things on a scale that is very, very small. We've been talking about things on an atomic scale, where we're only talking about a couple atoms, one molecule, things like that. But in order to actually use or talk about things on a scale that we can measure with everyday devices, we need to actually use many, many, many molecules or atoms. There is a convenient number that chemists use, a very convenient number that chemists use to talk about everyday quantities of substances. And that convenient number is a mole. Now, a mole is a number very similar to a dozen. So when we say we have a dozen something, say we're talking about atoms, say we're talking about oxygen atoms. If we have a dozen of these, what we're saying is that we have 12 oxygen atoms. Okay? If we have a mole of these, what we're saying is that we have 6.0221421 times 10 to the 24 atoms of oxygen. And so this many atoms of oxygen actually has a normal weight, a weight that we can measure with most devices, most mass measuring devices. Versus 12 atoms, we'd have no devices that could actually measure that amount of mass. And so the way it works is that if you have a particular molecule, say water. Water has an atomic mass, or excuse me, a molecular mass of 18.0 AMU. If you multiply this by this number, remember this is kind of like a dozen. If you multiply it by this number, you actually, if you have that many water molecules, you will end up with 18.0 grams. Now notice the similarities here. 18.0 AMU, 18.0 grams. And so this many water molecules weighs this many grams. And so it gives a very, very convenient conversion between molecules and grams. If you can say, well, instead of just taking one of those, I'm taking an Avogadro number of those, like a dozen of those. Okay, so dozen is a fantastic analogy because we know what that's like. But since this is such a bigger number, let's go ahead and practice this a little bit more. So consider this. By definition, these are the masses in grams of 1 mole of a substance, 1 gram per mole. So the molar mass is the mass of 1 mole of that substance. Okay. The molar mass of an element is the number for that element that we find on the periodic table. Okay. So the molar mass of an element is the mass number for that element that we find on the periodic table. If we're talking about average mass numbers, remember those atomic weights on the bottom, the molar mass for that particular element, not just that isotope, but that element type is just that atomic weight underneath. So the formula weight in AMU will be the same number as the molar mass in grams per mole. Okay, so the formula weight for any particular formula, no matter whether it's ionic or molecular, in AMUs will be the same number as the molar mass in grams per mole. So if we have 1 mole of oxygen, we have 32 grams of oxygen. If we have 1 mole of water, we have 18.0 grams of water. If we have 1 mole of sodium chloride, we have 58.45 grams of sodium chloride. Now, if we had 1 molecule of oxygen, we would only have 32.0 AMUs of oxygen. We only have one oxygen molecule, so that only weighs 32 AMU. 1 molecule of water would weigh 18.0 AMU, and 1 molecule, well, it would be a formula unit, of sodium chloride would be 58.45 AMU. Now remember, 1 AMU equals 1.66054 times 10 to the negative 24. And so that's the conversion that we go from AMU to grams. So consider this idea right here. So for water, if the atomic weight of water is 18.0 AMU, we multiply that by the conversion between AMU and grams, so grams divided by AMU, and then multiply that by Avogadro's number. This is the number for a mole shown on the last thing, 6.022 times 10 to the 23. So we got molecules of water per 1 mole of water. We end up with the same number with just different units. And so we can convert very rapidly between anything in AMU to grams per mole. So this is very, very useful, a useful table from your textbook. It reminds you the relationship between molar mass and formula weights. So atomic nitrogen, okay, the formula for atomic nitrogen. It's got a formula weight of 14.0. If we look at the periodic table, that's the number underneath nitrogen to the first decimal place. That would have a molar mass of 14.0 grams per mole. If we go to molecular nitrogen, which is how we normally find it, remember molecular nitrogen has 2 nitrogen atoms. Those 2 nitrogen atoms would weigh 28.0 AMU, and if we had a mole of nitrogen atoms, it would weigh 28.0 grams. So over here we have one more column that is kind of interesting. So the number and kind of particles in 1 mole. So if we had this atomic nitrogen here, if we had 1 mole of those nitrogen atoms, this is how many nitrogen atoms we would have. If we had 1 molecule of molecular nitrogen, or excuse me, 1 mole of molecular nitrogen, we would have this many molecules, but we would need to double that because there are 2 nitrogens in the formula unit if we were going to talk about the number of atoms. So this table, make sure you kind of look over this table, this 3.2 in your textbook, and realize how these numbers are relating to each other.